Well, I'd say it's been a pretty crazy semester with all of our classes moving online. It's certainly not something I think any of us expected when we started at the beginning of the spring semester. But here we are at our last lesson. We're going to talk about doing definite integrals using the substitution technique. Uh, if you've already watched the previous video, then we've talked about how to do indefinite integrals using USub. And that's what we have on the board here. We have an indefinite integral where when I look at this, I don't know the antiderivative of this thing off the top of my head. It's not something that's on my list of basic derivatives or antiderivatives that we uh, have memorized by now. So when I see something like this, I should be thinking, okay, how can I turn it into something I know how to handle? Right? And the technique that you learned in the previous lesson is the substitution technique. Um, those of you who are going on to Cal 2, you'll learn a handful of other techniques for handling integrals that you don't just automatically recognize from your list of derivatives and antiderivatives. But the substitution technique is pretty useful. And here, the thing that kind of tells us that we want to use it is we kind of have, first of all, a composition of functions here. I have a square root function, and then I have something else on the inside. I have this x cubed plus 1 on the inside. All right, so this is a composition of two functions, and notice that this inside function, the x cubed plus 1, the derivative of that, or close to the derivative of it, shows up outside the square root. The derivative of x cubed plus 1 is 3x squared. We don't have a 3x squared, we have a 4x squared, but that's close enough. If it's just off by a constant, we can work with that. All right, so judging from what we've seen in the previous video, it looks like we would want to let u equal x cubed plus 1. But this isn't supposed to be a repeat of that video. This is supposed to be a lesson on how to handle definite integrals using USub. All right, so let's turn this into a definite integral. Let's do the integral of this thing going from -1 to 1. All right, so we'll start out basically the same way with setting up our substitution as we did with the indefinite integrals. But then I'll explain to you guys how to handle these bounds on the integral. We know that with these definite integrals, our final answer shouldn't be some function. Our final answer should be some number. That number, typically we think of it as representing the area under the graph of this thing, whatever the graph of this thing looks like. I don't even know what the graph of this looks like off the top of my head, but that doesn't matter. We can still find the answer to this integral. All right, so let's get into this. We've got the integral from -1 to 1, and the thing under the square root, we're letting that turn into a u, so I've got the square root of u. But then I have this other stuff that I need to figure out what to do with, this 4x squared dx. All right, now if I come over here to my substitution and take the derivative of it, the derivative of u with respect to x is just 3x squared. Now, I have a 4x squared dx, and something you saw in the previous video, if we move this dx over to the other side, then we have du equals 3x squared dx. And really, I want this, I guess I want a 4x squared dx, so how can I get that? Well, let's get rid of this 3. So if I divide both sides by 3, I have x squared dx equals 1/3 du. So that's a little bit better. I have an x squared dx. Let's go ahead and make it a 4x squared. Another option would be to just take this 4 and move it outside the integral and not even worry about it until the end. But let's go ahead and get the 4 involved here. If I multiply both sides by 4, then 4x squared dx equals 4/3 du. All right, so now I have everything I want showing up in the rest of my integral. I have a 4x squared dx showing up, and so this is going to tell me how to handle this 4x squared dx. 4x squared dx turns into 4/3 du. All right, now I have this new integral in terms of u, and I actually have a problem with what I just wrote down, and this is going to be the main point to this lesson. The problem with what I just wrote down is that this -1 to 1 in our original integral, those were the x values. X is starting at -1 and ending at 1. All right, so x goes from -1 to 1. This integral doesn't deal with x's anymore. This integral deals with u's. And so I can't have x's here either. These are x values. I don't want x values, I want u values. All right, so if you wrote the -1 and 1 on this integral, sorry to, I guess, trick you like that, but we need to figure out what numbers belong here. All right, so let's come back to our original numbers. If x is -1, what should u equal? Well, come back to our substitution. U equals x cubed plus 1. So u equals x cubed, -1 cubed plus 1. -1 cubed is -1. All right, so for this lower bound, when x equals -1, our u actually equals 0. All right, so if I'm doing this integral with respect to u, then instead of a -1 down the bottom, my u value starts at 0, not at -1, it starts at 0. Okay, let's do the same thing up top. X equals 1 was my upper bound. And again, let's go back to our substitution. U equals x cubed plus 1. So we'll use this substitution here to figure out what our u value should be on this upper bound. All right, so u equals x equals 1. So 1 cubed plus 1, which is 2. When x equals 1, our u value equals 2. So now our upper bound is 2. All right, so this is how we're going to handle these definite integrals using substitution. Whenever we make the substitution, u equals x cubed plus 1, and it's a definite integral, we have to make sure we adjust the bounds on the integral as well. Okay, these bounds were x values, but if we're doing a u integral, we need u values. All right, so we use our substitution, x cubed plus 1, to find our new bounds on our integral. All right, so from here, this is a simple antiderivative, okay? And that's the whole point to use substitution, is we take an antiderivative that we don't know and turn it into something we do know. All right, so let me just clean things up a little bit, make a little bit more room for us to work. Let me move all this down here so I have more room for my integral. All right, so let's finish our integral. First of all, I see this 4/3 du. 4/3 as a constant. When it's being multiplied inside our integral, we can bring it outside the integral, so I'll just bring the 4/3 out. 4/3 times the integral from 0 to 2. And we don't like to think of square roots when we're dealing with derivatives or antiderivatives. I'll write this as u to 1/2. And now again, this is just a simple antiderivative, right? This is just u raised to the power, so we use our integral version of the power rule. So I need to do 1/2 plus 1, u to the 1/2 plus 1, that's, let's see, u to the 3/2. And then I need to do 1 over that power, 1 over 3/2. All right, and we're going to evaluate this from 0 to 2. Now 1 divided by 3/2 is just 2/3. So let's clean that up a little bit. This is 4/3 times 2/3 times u to the 3/2 evaluated from 0 to 2. Let's clean this up a little bit more. 4/2 times, or 4/3 times 2/3 is 8/9. And then here I need to, fundamental theorem of calculus says I need to plug in the 2, plug in 0, and subtract. So I've got 2 to the 3/2 minus 0 to the 3/2. Obviously that's 0 to the 3/2 is 0, so we're left with just 8/9 times 2 to the 3/2. And I don't know, maybe 8, that's 2 cubes. So then I could do 2 cubed times 2 to the 3/2 and clean this up a little bit more. I don't really care. This number here, whatever this number is, it's going to be some ugly decimal number. This number represents our final answer. It's our area under the graph of this function that we started with in the integral. Okay, so bottom line, main idea, you're going to go through kind of the same routine that you had for your definite integrals, where you do your antiderivative, plug in your bounds, and subtract. Okay, so that part doesn't change. You're also going to go through kind of the same routine that you went through with u substitution. The only thing that's new here in this lesson is whenever we make our substitution, if it's a definite integral, we have to update the bounds because the bounds start out as x values, but we need to update them to be u values. Okay. So I've got a couple more examples to run through with you guys. I'll go through those a little bit more quickly. And maybe it would be a good time for you to pause the video and try this yourself. All right, so here's the next example, the integral from 1 to 2. And again, this is an integral. Here it's z instead of x, but that doesn't really matter. So z is starting at 1, z is ending at 2. And here, if you don't do this already, I recommend doing something to distinguish between your z's and your 2's. Otherwise, it can be really confusing, all right? So anytime I write a z, I have this bar on it, just to make it clear. Now, pause the video here, think about what substitution you want to make. And one thing I'll mention, look back at this last example, we had an x cubed plus 1, and that's what we let u equal because we had an x squared showing up somewhere else. Look at this, we have a z cubed plus 1, we have a z squared showing up. So maybe it's kind of clear what the appropriate substitution here would be. All right. So go ahead and pause the video here, try this yourself, and then press play and see how you did. All right, so we're going to let u equal z cubed plus 1. And if it helps, let me do this real quick. Sometimes it helps students to see this written in separate pieces. I'm going to rewrite this. Instead of z squared over z cubed plus 1, I'm going to move that z squared off to the side. So this is times z squared dz. All right, so just having things kind of broken apart here and having this z squared over here next to the dz, I think helps students see what's going on when they're first learning this sometimes. All right, so now let's do our substitution. U equals z cubed plus 1. So my integral, I've got 1 over, this whole thing turns into u. All right, now we need to figure out what happens to this z squared dz. And we figure that out by doing the derivative over here. The derivative of u with respect to z is 3z squared. So then du equals 3z squared dz if I move that dz over to the other side. And again, this basically matches this z squared dz. The only thing is I have this extra 3 hanging around, so to get rid of that, I'll move that to the other side, divide both sides by 3. Z squared dz equals 1/3 du. All right, so this piece of my integral, the z squared dz, turns into a 1/3 du. Now the last thing I have to do is update my bounds. These are z values. I need to figure out what the appropriate u values are. All right. So again, come back to your substitution. If u was z cubed plus 1 and z, this lower bound was 1, z was 1, well, in that case, u would equal 1 cubed plus 1, which is 2. All right, so when z equals 1, this lower bound, the appropriate u value would be 2. All right, and then in the same way, the upper bound was 2. All right, so let's see what happens there. If z is 2, then again, using our substitution here, then u should be 2 cubed plus 1. That's 8 plus 1 is 9. So this upper bound, when z is 2, the u value is 9. So my upper bound now is 9. All right, so now again, from here, it's a pretty straightforward integral. If you like, you can bring that 1/3 out. 1/3 times the integral from 2 to 9 of 1 over u du. And now, again, this is one of our basic antiderivatives that we should know. The antiderivative of 1 over u is the natural log of not just u, but remember, natural log of absolute value of u. All right, so if you did this on your own and you forgot the absolute value, make sure you put that in here. Natural log absolute value u. And I need to evaluate this from 2 to 9. So I have 1/3 times natural log of absolute value of 9 minus natural log of absolute value 2. Now in this case, I emphasize that absolute value, but in the end, notice the absolute value of 9 is just 9 because 9 is already positive. The absolute value of 2 is just 2 because 2 is already positive. So for your final answer, it would be okay in this case to write this without the absolute values. 1/3 times natural log of 9 minus natural log of 2. And again, there's lots of different ways I could write this using properties of logarithms. I'm not really concerned about any of that. This is some number. You can punch this into a calculator and get some ugly decimal number. I don't want that ugly decimal number. I just, this is an exact representation of your answer. Whatever this ugly decimal number would be, that would tell us the area under this function, z squared over z cubed plus 1 between 1 and 2. All right, so this would be my final answer, or whatever version of it you want to write down using your log properties. All right, so let's finish with one that looks really ugly, but after we make the substitution, it turns into a really easy integral. All right. Now again, I'll have you do this yourself, but just kind of, if you're not quite sure how to start here, again, I think it helps people sometimes to write these fractions in separate pieces. So the top is the sine of square root of x. And then I'm dividing by 1 over the square root of x, so that's the same thing as times 1 over the square root of x. Okay, And the order doesn't matter in multiplication. I could have written the 1 over square root of x first and the sine of the square root of x second. If you're just multiplying, then order doesn't matter. All right, but the reason I did that, the reason I broke this fraction into these pieces like this is because, again, it helps us see what the appropriate substitution is. Whenever you're first learning the substitution technique, it's one thing to watch us do it in these videos, but then suddenly when you're doing it on your own in your homework, you're staring at this integral and you're wondering, okay, what in the world do I do here? What's the right substitution? In the video, they told me what substitution to make. Now I have to figure it out myself. Little things like this, rewriting it, can help you figure out what those substitutions should be. The other thing I'll tell you is when you're first learning this, there's going to be some trial and error involved. You're going to say, okay, I think I know what to do. I think I know what you should be. And you're going to try it and realize that it doesn't really turn into anything that you know how to handle. It doesn't really lead anywhere useful. Okay, if that happens, don't worry about it. Maybe you picked the wrong thing for you. Okay, so go back, see, is there something else I could have picked for my substitution? All right, so as you're learning these things for the first time, this is just part of the natural part of the learning process. So don't get worried when you run into those mistakes. Just go back and try something different. All right, and as usual, if you get completely stuck, don't be afraid to reach out to me, and we can go over it during office hours or something. All right, so anyway, back to this integral. Pause the video here and see if you can do this integral on your own. See if you can figure out the appropriate substitution. Again, I know I need to do some kind of substitution because when I look at this thing, I don't know the antiderivative of this off the top of my head. It's not something that's in our basic list of derivatives and antiderivatives. All right, so we've got to have some different way of handling it. And at this point, the nice thing in Cal 1 is we've only got one option. It's the substitution technique. Again, in Cal 2, you'll learn several others. All right. But anyway, pause the video, try this on your own, see what you can come up with, and then press play to see how you did. All right, so I think when I look at this, when I'm trying to decide what substitution to make, one thing to keep in mind is this is kind of related to the idea of the chain rule with derivatives. I have this composition of functions here, sine, and then I have a square root function, square root of x on the inside of the sine function. So one of the things to look out for is when you have a composition of two different functions, a lot of times whatever is on the inside is going to be what you want u to be. The other thing to look for is there anything in this integral where when I take the derivative of it, I get something else in the integral, all right? And it turns out that this square root of x works out perfectly because it kind of satisfies both of those criteria. It's on the inside of my sine function, and look at what happens when I take the derivative of it, all right? So u equals square root of x. So what's the derivative of that? The derivative of u with respect to x. Remember, this is x to the 1/2 power, so I just need my power rule. 1/2 x to the negative 1/2. Okay. Now, if I leave it written like this, maybe you don't see how this is useful, but I can rewrite this with a positive exponent. This is 1 over 2x to the positive 1/2. And so I have, again, my usual thing, I want to move the dx over to the other side. So I've got du equals 1 over 2 x to the 1/2, which is square root of x, dx. Okay, so now look at what we have here when we take the derivative of our substitution. Taking the derivative, we almost have this extra piece perfectly. 1 over the square root of x dx, 1 over 2 times the square root of x dx. The only thing that I don't like here is this 2. But again, we've already learned that if our derivative is off by a constant, we can compensate for it or fix it. Here I can multiply both sides by 2 and everything works out. If I multiply both sides by 2, the 2 on this side goes away. And then I have 2 times du. All right, so now this is exactly what I want when I make a substitution. U is going to take the place of this inside function, and then the derivative of that inside function shows up out here. All right, so this is the perfect setup for substitution. This is exactly what we want. So this will be a pretty easy integral. The only thing we have left to do is we have to update our bounds, right? This was the only difference in this lesson from your previous lesson on substitution, is now we have to figure out what our new bounds are. All right, so again, our substitution is we're doing the square root of x. All right, so let me write this down over here. Originally I had x equals pi squared over 4 for my lower bound, but u will be the square root of that. U equals the square root of pi squared over 4, which is just pi over 2. All right, so my new lower bound is going to be pi over 2. All right, let's figure out the upper bound as well. The upper bound, when x was originally pi squared. All right, so when x is pi squared, u is the square root of x, so u is the square root of pi squared, which is just pi. So that's my new upper bound, is just pi. And I'm also realizing I forgot to write the bounds on this integral here. Here I still have x's, right? If I still have x's, then I still have my x values for my bounds. That was pi squared over 4 and pi squared. All right, forgot to write those down. All right, well, let's write down this integral that we have after our substitution. All right, now we're going to write everything in terms of u. We've already got the bounds updated in terms of u. Now u is going from pi over 2 to pi. Sine of square root of x. Well, what was square root of x? That's where we started. That's u. So now I have just sine of u. And then we went all through all this work and figured out that 1 over the square root of x dx can just turn into 2 du. So this whole thing here turns into just a 2 du. And again, this 2, I can just bring it outside my integral. This is 2 times the integral pi over 2 to pi sine of u du. And now this is a very basic antiderivative. You do still have to be careful though. We know that the derivative of sine is cosine, but we're not doing the derivative, we're doing the antiderivative of sine. So we have to think backwards. What do I take the derivative of to get a positive sign? So I would actually need a negative cosine here. 2 times negative cosine of u, evaluated from pi over 2 to pi. Right, the derivative of negative cosine is positive sine. This negative sign just make things a little bit cleaner. That's a constant that can be brought out front. So I'm just going to write this as -2 out front and then apply my fundamental theorem of calculus. I've got cosine of pi minus cosine of pi over 2. All right, and if you stop and think about the unit circle for a second, pi is that 180-degree angle. The x value over there on your unit circle is -1. So -2 times -1 minus cosine of pi over 2. Pi over 2 is that 90-degree angle. The x value there on the unit circle is 0. So cosine of pi over 2 is 0. So we've got -2 times -1, which is a +2. Now here's the crazy thing about this integral. we started with, this is probably the ugliest integral we've done in this lesson. The integral of sine of square root of x over square root of x from pi squared over 4 to pi squared. But our final answer was just a simple old number 2. All right. So again, all this means is that if you were to graph this function and find the area under the graph of this function, whatever that thing looks like, the area under the graph of that function over this interval would just simply be 2. All right. Which it seems strange, coming back to these other examples. Here, if you punch this into a calculator, you get some ugly decimal number. The second example, we've got these natural logs. That answer is going to give you some ugly decimal answer. But here in the end, the ugliest looking integral that we had all along gave us the nice clean answer too. Anyway, that's it for this lesson. So I'll post that last homework assignment over section 5.6 to let you practice these things. And if any of those give you trouble, feel free to reach out to me and I can help you out.